Okay, welcome to part 3 of our lecture video series for Wednesday, May 3rd, where we talk about the ideal gas law. So, in order to understand the ideal gas law, let's first define an ideal gas. And in fact, you and I have already discussed what an ideal gas is because we've been thinking about gases under the kinetic molecular theory or model of gases. So, an ideal gas is simply a gas that is modeled well by the kinetic molecular theory. So a couple of reminders about kinetic molecular theory. Yes, we've got collisions and they're elastic collisions, right? But more importantly, when we're thinking about an ideal gas, we're thinking about there being no intermolecular attractions, repulsions, interactions that are happening between gas particles. And we are also assuming that our gas particles take up no space, meaning that the volume of the container is the volume that our gas is occupying. So we don't have to subtract out any correction for the fact that our molecules themselves are taking up some of that space. And very sneakily, you and I have actually already derived the ideal gas law by looking at our pressure relationships to volume, temperature, and moles. So this equation here, PV over NT is equal to a constant. This is actually the ideal gas law, where specifically that constant is known. So PV over NT is equal to R. This is the ideal gas law. Meaning this equation describes the behavior of a gas that can be modeled by the kinetic molecular theory. Don't know why I feel like I'm running out of colors. All right, so ideal gas law. Now, some things about the ideal gas law. You could also see this written in the form that most people are familiar with. Like, this is how I learned the ideal gas law, which is moving the NT over. So they get PV equals nRT. That's another way of looking at the ideal gas law. It's just a re-expression of it. However, I actually like the version that I've boxed originally because to me, that shows all of those mathematical relationships, meaning the direct versus inverse proportionalities that exist between our gas properties, all in one place, right? I don't have to think too hard about it. But both of these are expressions of the ideal gas law. Whichever makes more sense to you, feel free to apply it. So let's talk about the components of the ideal gas law. So P, of course, is our pressure, but our pressure is going to be in atmospheres. So if you want to apply the ideal gas law, you need to ensure that your pressure unit is in atmospheres. V is our volume of our gas, which is going to be equivalent to the volume of our container because we are an ideal gas in the ideal gas law. And this is in liters. N, of course, this is our moles of gas. And T is the temperature of our gas, and this is in Kelvin. So just a reminder, Kelvin is whatever your Celsius degree is plus 273.15. Now this brings us to the proportionality constant, R, that relates all of these variables. This is called the gas constant. And using all of these units put together, moles, liters, atmospheres, Kelvin, this is 0.08206, and the unit is liter atmosphere per mole Kelvin. So I remember this by like phonetically like sounding out what this sounds like, latum per molk. So you can remember that, liter atmospheres per mole Kelvin. And this is something that I highly recommend that you memorize. Again, I will give it to you on exams, just like I promised I would give you like the specific heat capacity of water on exams, but you're going to be using this constant so much that just knowing it off the top of your head is going to be a real big time saver for you. So, for example, what volume does 1.00 moles of a gas occupy at standard conditions? So let's remind ourselves about what standard conditions means. So we talked about standard conditions when we were looking at our standard heats formation. Sorry, had a little brain freeze there. So let's go ahead and remind ourselves of what those are. So standard temperature in the case of gases is, let's see here, 0 degrees C or 273.15 Kelvin. When we were talking about thermodynamics, it was 25. It's just kind of, that's a little difference there. And then standard pressure is exactly 1.00 atmospheres. And I want to know what volume. So what volume? So I'm going to start by making an assumption that my gas is ideal. So that's PV over NT is equal to R. And since I want to find my volume, that is my variable of interest here, I'm going to go ahead and rearrange this equation by multiplying both sides by NT and then dividing both sides by P. So doing a little bit of algebra right off the bat, this gives this gives me nRT over P for my volume expression. So if you need to pause and verify that for yourself, feel free to do so now. All right, now that we have this rearranged, let's use this ideal gas law to figure out the volume that 1 mole of a gas occupies at standard conditions. So for gases, these are your standard temperature and pressure, STP. Okay, so this is equal to N, so I told you it was 1.00 moles of a gas, times R, this is our gas constant, so 0.08206 liter atmospheres per mole Kelvin, times our temperature, which is 0 Celsius or 273.15 Kelvin, over standard pressure, which is 1.00 atmospheres. Let's kind of check our sanity with some unit analysis here. So moles and per moles will cancel. I have atmospheres over atmospheres, which will cancel, and Kelvin and per Kelvin, which will cancel, leaving behind liters. That's good. So I've got 1 times 0.08206 times 273.15 divided by 1. This equals 22.414689 liters. And then since we've got 3 sig figs here, volume is equal to 22.4 liters. And in fact, this is a good thing to know off the top of your head. 1 mole of any gas at standard temperature and pressure occupies around 22.5 or 22.4 liters of space. Okay, so that's an application of the ideal gas law. So we have done the ideal gas law, and up next we are going to look at another property of gases, which is Dalton's law of partial pressures. And then I think we might have a little bit of time to then use Dalton's law of partial pressures and what we know about the ideal gas law to maybe do a little bit of a kind of challenge problem where we put our knowledge to the test. So let's at least get through partial pressures, and then let's see if we have time for another example.